and 13, 14, the quantification of separability of the convex-compact subgroups of right and of groups via representations.
Okay, so the previous two talks were very, very good and very helpful in terms of definitions. So, okay, I'm going to talk about separability. It is also the residual property. So, what means that so the group G is separable, the subgroup H, G, the H is separable. If for any element G, which belongs to G but not to H, there exists a homomorphism from G into a finite group U, that which separates this element from the image of the subgroup. So basically, what is residual finiteness? Which was discussed before. Residual finiteness just means that the trivial subgroup is separable. Right? So like for every element which is not equal to 1, there exists a homomorphism into a finite group such that the image is non-trivial. Another way we can say that H is separable if H is the intersection of finite index subgroups finite index and L contains H. So intersection of all finite index subgroups containing H. I don't know, I think it probably was Maltsev or other people who first start considering separability. So initially, separability was considered as a useful property for solving algorithmic problems, like residual finiteness. So Maltsev noticed that that if the group is residually finite, then the word problem in this group is solvable, because if a finitely, let's say finitely presented or finitely generated with recursive presentation group, if it is residually finite, then the word problem is solvable, because you run two algorithms, one enumerates consequences of defining relations, another enumerates finite quotients, and if your element is equal to 1, you get it in the first process. If it is not, you get it in the second process. You get a finite quotient, but this element is non-trivial. The same thing, like separability, if H is separable, then the membership problem in H is decidable the same way. So you run two processes and by the way, so the results are all joined with Alinov-Dorin. Mostly results today are joined with Alinov-Dorin, and some results about limit groups, which I'll talk about in the second half of the talk, are joined with my student now, he's a former student, Tina Brown. Okay, now, and then recently, separability played a crucial role in low-dimensional topology in connection with virtually Haken and virtually fiber conjecture. So when Agel proved the conjecture of Weiss and proved that like every cubical hyperboreal group is virtually embeddable into RAM. Like in group theoretic terms, it is that. What exactly are proved. Now, and Now, cubically convex-cocompact subgroups of RAAGs are separable. But maybe I should give some definition. So first, RAAG is kind of nice. Right angle arching group. So we have a graph gamma. For example, let me just start with consider an example of something great. So suppose you have a graph of three vertices, denote this vertex by A, this by B, C. So the right angle arching group corresponding to graph gamma is a group given by the generator subvertices. And we have commutativity relation for any two vertices, which so here we say that the CB is the same as B. For every H, we say that corresponding vertices converge. So this is right angle arching group. Now, this is a fundamental group of so-called Salvetti complex. Salvetti complex of right angle arching group, let me do it like this. Okay, let me just define it for this example, but now I need colors. Which color? Red. Yeah. So B is going to be red. C is going to be green. So like, for example, for this group. So we have one group for A, and then we have a torus. This. And right? The fundamental group of such a complex is exactly like has relations that C commutes with B and nothing else. So for every basically, so we can just for every right angle arching group, we can draw loops corresponding to generators and then put squares everywhere for commuting generators. And then if we have a boundary for cube, we add a cube and so on. So this is a Salvetti complex. Right angle arching group. Okay, now returning to separability. Marshall proved that finitely generated subgroups of a free group are separable, right? And actually, he proved more that if H is a finitely generated subgroup of a free group, then there exists a finite index subgroup A. Index such that H is a free factor in K. H and let's and the proof is very simple, and since I'm going to do something very similar for right angle arching groups, I'll just give an example. So let's take as H, let's take a Storing's graph, which Andrea was talking about. So just take a cyclic group. And a free group of these two generators. Let's say B. A, maybe another B. Let's do it in this. So this means that H just a cyclic group square A B inverse. So how do we find this subgroup B? So what we can do? Okay. So we complete this graph. So this is like in terms of like which Andrei was using. So this is a core graph, right, of the Schreer's graph of the subgroup H. Like if this is a coset corresponding to H, then this is a coset corresponding to AH, A square H, and so on. So what we do, like for every label, now there are two labels here, A and B. We consider a connected path labeled by A. And then we complete, like we draw an H labeled by A from the terminal vertex of this path to the initial vertex of this path. Then the same we can do for B. And B. Right. And this is a core graph for this K. This K. And moreover, we can see that, you know, edged loops in this graph. Basically, so there was one loop and we added what, 1, 2, 3, 4 loops. Edged loops means just adding the free generators to the to H. So H is this K is a free product of H and 4 generated free group. And it has finite index because this is actually a Schreier graph of K, right? At each vertex we have, no, I have to do something else. Sorry, so this has valency. I have to, so it's not 4. I have to add loop labeled by A here and loop labeled by B here. Okay, now every vertex has valency 4. So basically it is a graph of cosets of certain subgroup, of a subgroup generated by these loops. But it doesn't have, it's not 4 generators, it's 6. We added 6.
Вы?
So this is a
О, привет.
canonical completion of
Да, у тебя крутой чемодан.
finite index subgroup K.
В прошлый раз у тебя было вообще... Тут это Харлампович выступает.
Ты сейчас слушай.
Now,
Ну так, я опоздал.
Ну, мне было бы интересно, ничего.
Хочешь послушать?
Да нет, я сейчас
proves that
в туалет у вас схожу, а ты это
Да.
по дороге.
А я думал, что ты уже внутри
so
сидишь.
compact.
Ну что, купил карточку?
Нет, ну где я уже там? Я ну, посмотрел вроде. Нет, там
Не спрашивал.
знаешь, можно где купить. Вот там, где я тогда купил рядом с Максимом, этот магазин арабов. Они когда хороший купил,
Ну ты купишь, да?
не надо было это там. Ничего я потом оттеряли, они никаких документов не попросили, ничего. 20 евро всего.
Ну хорошо, да. Это лучше, чем с этим фри связываться.
Да, конечно.
Может, ты кофе хочешь?
Я кофе хочу, я 32 час уже еду, без
Ну,
нас. У тебя в туалет.
Ну я так промою эти чашки этой водой, которая у меня есть.
Okay, now what am I going to do here? So one more kind of introductory definition. Or maybe I should first say what is convex-cocompact. So first of all, so a subset is of geodesic metric space is K quasi-convex. If for every geodesic, say, space X, so if you have a geodesic, this is my subset S. If I have a geodesic with points, final points, or like initial and terminal points in S, then it is, this geodesic is in the K neighborhood of X. Okay, so this is what means quasi-convex. A quasi-convex subset. Now, a subgroup is a quasi-convex acting on some geodesic metric space in the orbit of each point by the subgroup is a quasi-convex. Now, in our terminology, yeah, so if you have right angle arcing group, then we always have a Salienti complex. So we have a cube complex. Now, cube complex, okay, so it's a set of cubes of different dimension, which are attached to cubes of length h length 1 attached to each other by corresponding like common subcubes. Like cube complex. Like this. Square, H, something like this. This is the cube complex. So Salienti complex is a cube complex. And the fundamental group of Salienti complex is exactly this right angle arcing group for which we constructed it. Okay, now if you have a cube complex, it is a geodesic metric space. But there are several metrics. It can be, it is usually, it is a cut, if it is a cut zero cube complex, there is a cut zero metric. I'm going to talk about word metric, meaning that, okay, so we just go along the edges of cubes. So this is my geodesics along the edges of cube. It is the same as word metric. Standard generators. With respect to standard generators. Now, if the group happen to be hyperbolic, like for example, the subgroup of RAAG happen to be hyperbolic, then we can talk about, then actually does not matter what kind of generators we take, like quasi-convexity doesn't change if we change generators. But for right angle arcing groups, if you have standard generators, I'm only talking about like quasi-convex subgroups in terms of like, this standard generators, because it is not known actually. So sometimes it's known we cannot change generators, but basically this is kind of a gray area. But it is not known whether we can change generators to what we can change them to preserve quasi-convexity. Also, if we have, so we talk about absorbed quasi-convex subgroups of RAAGs. This is the same as zero quasi-convex, and this is the same as cubically convex-cocompact. Like, so I won't give a definition. Like, it means that there is a closed compact set reserved by the group, and the reaction is cocompact. This is the same as cubically. Still didn't formulate the results and didn't prove them. So, okay, the same Maltsev. Like what Maltsev actually noticed? Maltsev noticed that linear groups are residually finite. And finitely generated subgroups of linear groups, they're close and there is.
Ну, что она мне говорит, что она в Лиле? Я написал, что в Силу. Она?
В Лиле. Это, ну, похоже.
Now, why, how to prove that the linear group is residually finite?
Одну
You have
программу
a set of matrices.
Потому что она мне говорит,
Or some field.
она мне
Okay,
показывает
massive
этапы
group
не
that basically,
через автобан.
like if you only take
А как-то, блин,
finite set of
я знаю.
matrices, we consider
не,
matrix
ну я не хочу, я хочу
entries,
через автобан
then we
ехать.
can talk about,
До центра.
so we have to
И
take
Я
a
съезжаю на
finite algebraic extension
Да,
of
как
Q,
начал
and then take a finite
там,
purely
где как
transcendental
съезжать.
extension of
Вот,
Z.
такой
да, есть.
Then we
Лефевр,
consider finite number of
правой
matrices, so
ноги,
finite number of
мимо
pairs.
налоговой
Then
конторы.
only
там.
finite number of
Да,
elements,
Ну,
all
всё.
polynomials
Ну, отлично.
have to be
Ну, там
Вот,
invariant.
возьмешь?
Then basically, I'm talking about field of characteristics
Там,
zero.
вот это вот.
So basically, we sort of reduce the problem to matrices over C
Холодно, да.
over some ring, let's say.
Еще более.
Ну, с другой
Let's
стороны,
talk
когда
about
не
matrices
даже...
over C, like,
Так
for
они-
example,
Пать, там вообще невозможно.
then we can send
У нас
C,
зубр, конец апреля, и такой зубр.
just include some
Так, сахар вон.
finite.
Может быть, даже твой этот еще где-то есть.
А я-
But we have to make sure that the matrix which
Да,
we
не
don't
хочется
want to
сейчас.
Подожди,
keep,
подожди.
that the
Давай,
entries
давай,
are
Я
reducible
тоже.
by this P.
Вот.
So that we
Ну,
just
ты там,
don't
еще
keep
должен-
the
ну, там вроде
matrix
магазин у тебя есть
which we-
какой-то, да?
which we don't
Там
want.
магазин совсем рядом. Но он
But
такой-
the homomorphism
Yeah.
of rings
Я успею, если мы все
is
сделаем.
extended to the homomorphism
Да,
of
Может быть,
matrix
такой
groups.
вариант, как я типа...
Ольга,
So
да,
basically, if we have a
Ну, сейчас
set
у меня
of
звук
matrices over some ring,
У меня звук.
if we map this ring
Я
to
тоже
a
пришел
finite
после
ring,
пары, я
if you have
опоздал.
homomorphism,
Вот этот
then we map
зайки,
the
зайки.
group of matrices into a finite group.
И я
Then
начал.
if you don't want to kill some
Я,
element,
конечно, потерялся.
then okay, so we have to choose this finite ring in such a way that the corresponding matrix is not kicked.
Вот. Ну
And
и там,
here
конечно,
P
ну это,
should be just
он опять какую-то проблему.
large enough, like larger than all the entries.
Да, я видел.
Это компрессированный
Да,
и...
он это самое.
Okay,
Учитывая.
now about
Да. А мне
Да.
казалось, что
about
это...
topology, a couple of words about
Да, не знаю,
topology.
может быть. Но он,
Это
он-
грубо говоря, когда она не
Suppose you have an
складывается
algebraically
под
closed field, like
меньшего ранга.
Ну так это как раз проблема Ханна Нойман была.
Думаешь?
Ну,
Это обобщается, да?
где-то я это...
finite
Да, это
dimensional, like C vector space.
Нет, он сказал, что это эквивалентно тому,
Then,
что вот никакая подгруппа еще,
okay, suppose you
ее
have
вот такой
homomorphism.
тоже компрессор. Вот
Ага.
что она сама компрессит, но еще вот для любой ее подгруппы конечно порожденной тоже компрессит.
Но
Suppose you
свободно.
have a homomorphism of
Может быть, там с одним отношением
first
это тоже.
order gamma,
Нет.
general linear
Нет,
group.
ну за него отношения там даже гиперболиты. Понимаете, это
Ну да.
гиперболиты.
Okay, so then we have a subspace topology on
У меня, видишь, у меня на
row
компьютере звук
gamma
плохо работает.
induced by the risky
Она
topology of
Есть.
J.
Если ты можешь
Then
послушать.
we say that
Ну что, значит, мы едем вот по этому адресу, да? Ну вот твой,
Да.
ну на, возьми
the
контракт.
fallback of this
Распечатать еще
topology,
один.
fallback of this topology, we say
Ну
that
я
this is
тебе,
the
так сказать,
topology
тебя
of
адвокатом
gamma,
беру.
corresponding
Вон твой
to
ключ от твоего бюро,
representation.
ровно
This
напротив
is a
моего.
phasor
Моего
representation.
возьми.
Corresponding
Вон
to
там бюро, да?
representation of-
Ровно напротив.
А, ровно. Там же кто-то раньше сидел.
Okay,
Да, там, это для гостей. Нет, вон напротив. Вон на тетрадках.
so
Возле
now
гафа.
I can
Возле гафа.
formulate,
А, вот.
Ну не потеряй.
theorem,
Ты знаешь еще, там мы сохранились. Я
and
оставлял. Помнишь, я уезжал,
Да,
и
да.
тебе оставил место в этой
Как они выглядели, не
Ну,
помню.
такие вот, такая квадратненькая такая.
the word
Вот.
Слушай, я не помню. Ты купи новое, я тебе отдам.
Да ладно, я куплю, что там.
Сколько они стоят?
Ерунда. Вот, просто я, так сказать, сейчас очень интересно.
Ну, вообще, Витя, с меня 10, 11 лет.
После Дании. После выхода на пенсию, я понял, что это главное, так сказать.
Не, ну, слушай, если ты спортом занимаешься, вот это
Я
здорово.
бегу каждый день.
Ну, вообще,
Ну, когда нет, да, здесь.
ну, там в фивах ты можешь где-то бегать?
Причем не бегать.
А ты даже пешком ходишь, да?
Там от Филов до Ашана я доходил ровно до 40 миль от этого дома.
Я думаю, если с этим Жаном был не тот самый.
Нет, вот Жаном два. Два в месяц.
Но он так мне не позвонил, не пошел он к черту. С этим Максимом гораздо проще договариваться.
Corresponding to this row.
Витя, если не хочешь... А, ну мы машину положим. Почему?
Ну, конечно.
Ой.
Now, why it is good? Like,
Господи.
so there are several corollaries. Like one of them is like then
Это, я думал, что Петров это...
one can prove separability of H.
Sorry, but what did you mean exactly? So row H, the Zariski closure,
Все эти репорты, они, конечно, очень хорошо
H is the risk
сделаны.
closed.
Но
Like,
если
so
там
this,
было
yeah, this
людей,
is
там,
the risk
три, а лучше в 5 раз,
closure.
то ты не будешь разные передачи.
H is the risk
Там тоже.
closed in the
Толкота.
Хуже,
in
чем
L,
Чарли Боль, да?
in the
Ну,
topology
so you meant
corresponding to
the
this
bar on the other side, probably.
Торно там, где там как-то то налажено, более-менее ничего. Какие-то все тут работы, какие-то любопытные
Okay,
такие.
so that's the risky closure
Разговаривают.
Yes.
of this.
Слушай, сегодня ко мне вдруг пришел Радченко, его давно не было, он был...
But the intersection of row H of L and row H of H
Вот. И он предлагает, я ему сказал, что ты приезжаешь,
is going to be row
он
H of
предлагает
H.
пойти в ресторан в четверг вечером.
Ah,
Он пойдет со своей этой
I was trying to fix this in my mind,
girlfriend,
but
я не знаю,
yes.
но они уже давно
yeah,
живут.
that's
А нет, почему по-русски? Ну, их родной язык русский, конечно. Вот, вот, нет, ну там они могут. Вот, и она тоже математик, она у нас постдок.
Yes, so
Вот.
row H of H is the intersection of the
Алгебраически
closure in here.
so it's like row H of H is algebraically closed. It's-
Гомологическая
Yeah, so
алгебра.
Yes,
basically
Вот этот самый
that H
Линтон,
is given in L by finite number of polynomials.
я
That's,
был один
And
на
this is good
семинаре.
because
Я говорю, Даня, а что ты вот не пришел на
so H
Да
is
я был
defined
один.
like L is
Я
defined by
сидел
some
один, и просто неудобно. Я
finite
иду с
number
ним
of
в ресторан
polynomials
тоже.
here, and H is defined by some extra finite number of polynomials.
Да, да.
What is good
Я его
about that?
спросил,
Then
что-то
to prove
известно вот
separability
по
of
поводу
H,
границ.
then basically the
Но он мне
same
написал
what I
некий
wrote
обзор, могу
about
тебе
when
дать.
you talk about there is
Ну, например, он утверждает, я этого не знал,
the
что,
same multiple idea
что
is
вторая
going to
группа
work, like
гомологии,
basically
рацион-
you have to map your ring
она ранг не больше.
into a finite ring
Это как-то,
such a
ну
way
там
that
какая-то
one of these polynomials is not killed. Then the element doesn't like that
Конечно, вот это...
Ну, я тебе могу переслать его.
on the element. So then the element does not is not mapped into the image of the sub. Another
Ну что?
like one of the corollaries of this that you can actually quantify like this
Ну, я не знаю, что-
finite
Не знаю, на
portions.
самом деле,
I will write this later, but basically you can prove that
Значит,
that if you
ну,
fix
слушай,
H,
3000 с
then
копеечками. Там.
finite quotients to
Это,
separate
это,
elements.
понимаешь,
from,
это как раз то, что ты
L.
хотел, блин.
They
Ты не
all
взял
polynomially
рефлекс, да,
in,
но...
Да, а это я бы тоже
in the
так-
length of the element.
Да.
даже
Ну,
Like
там
to separate
какой-то обмен.
element G, you need a quotient
Жилая
of
площадь.
the size of the polynomial of G.
Она поменьше.
This is
Там было очень, да?
recently like many people like
И здесь, по-моему, тоже. Но это только жилая
Mark
площадь.
Hagen,
То есть это
Colin
туалет не
Borovik, who sort
считается.
of started this.
По-моему, коридор тоже
Many
не
people
считается.
did some different quantifications.
Ну, не
Там
знаю.
была.
Okay,
Я думаю,
so it's true
Слушай,
for
я выхожу.
right triangular triangle. Then
Ну, потому
another.
что, на самом деле, я сбежал, у меня пара была.
Okay, so then it is the same for L mutually special. This is a kind of very important class of groups, again, like in dimensional topology, basically means that L is a finite extension of the group acting nicely on a special group complex. In particular, it's true for hyperbolic trimanifold groups. Like so, the same. Hyperbolic trimanifold. And many classes of groups are virtually special. Now the same, this is always Brown. And it was actually proved earlier, the same for limit groups. But again, like I will try to talk about limit groups at the end. Okay, now what is the proof? Like, I mean, I did this beautiful picture, not for just. Okay, what is nice about word quasi-convex subgroups in right-angular groups? They and I will return to this example. They are fundamental groups of cube complexes, which are locally isometrically embedded into servative complexes. Now, what is local isometry? So it is locally injective map with the following thing. So if you have two edges, for example, coming from the same vertex, so if they are mapped like two edges, have file P1, file P2, which are since it's locally injected, they are different. Now, if they are bound a cube in subjective, like if they are on the boundary of a cube in subjective orbit, then it should be a cube here, which is mapped isomorphically into a cube here. So it cannot be that like just two edges are hanging here and they are on the boundary of the cube here. And the same thing for n edges. So this is what local isometry. Now let me give an example for the same servative complex. Green. Something like this. So A layer red, not easy. So this is B. And this you see over here. This is 3. As you can see, so every time we have CB, like there is a square here, right? Like for example, if I remove this square, it's not going to be locally isometric. It's not going to be local isometry into this cube complex. Okay, so and the following example is a combination of what Danny Weiss and Haglund and Hagen did, proving separability, following theorem. So that, yeah. Let gamma be a finite graph. Yeah. gamma be a finite graph. So let's go. Yes, solution of this. Why? Because the local is a metric. Local is a metric invariant. Into gamma. Into S gamma. So this means that y1 of y is a subgroup of y1 of S gamma, which is right angle function group. Then y can be in the so-called canonical completion. Yes, it is a finite power of this religion. Why? Okay. Now I explain like how it can be. So basically, I mean, this statement immediately implies that like that this fundamental group can be embedded in the fundamental group of a finite cover. And fundamental group of a finite cover of the stability complex has a finite index in the stability complex. Okay, now how we do this? How we do this canonical completion? Like I said, why then I didn't have enough space? Can be embedded in such a finite cover by completing the one skeleton of the complex. Completely exactly like in the case of a free group. Completing the one skeleton and then putting squares and cubes everywhere where there is a boundary of the cube. This I learned once from Miro Lazarovich talk. So we just do complete this string. We do complete else do this. So basically, I mean, I'm just completing the one skeleton exactly the same way as for a free group. Do I need something else? Yeah, right. Page 3. So basically, yes. And at least like there is a proton mark Hagen's paper that it interiorly all works. So that if you have a closed contour here bounding the cube, then it comes to the closed pre-image here. So to the closed contour, and then you can put squares and cubes everywhere. And this is all going to work together. Now this is, so you have to put, like, for example, here, you have to like put 4 cubes in here, because you have B and C, like if you have what C, B, C inverse, B inverse, okay, so we put a cube here, a square here, and so to each like contour of a cube of a square, we put a square. I am kind of talking cubes, but when we deal with fundamental groups, actually only squares are important, because the fundamental group of a square complex is going to be the same as the fundamental group if you like fix higher dimensions like in this square complex. Okay, so this is one thing. Now, what is important for us? Like after this completion, we can prove that we can obtain this fundamental group of this finite cover. You can obtain it from the group H by a series of H&L extensions with series of H&L extensions with the same associated subgroups and the same like identical isomorphisms between associated subgroups. And now, how will this work with the presentation? I mean, right now the left groups are linear, so there is some representation. Now we take another representation where all the stable letters will be added to the group. Is going to be sent, so like there is one representation, now we send all of them to the powers of where they were sent into the same first representation. So we have like two representations, then we can make a representation into the direct product of these two. And then H is going to be like, in the image of H, it's the only thing which is going to be in the diagonal. And the diagonal is the risky closed. So then you prove that for finite index subgroups, and then you take induced representation to the whole group because it's a finite index subgroup. Okay, now and a couple of words about limit groups. Like in limit groups, we actually prove more, and it's hard to prove like than this completion. We prove that the group is a basically this finite index subgroup is obtained again from the subgroup H by like we have to take a group obtained by series of extensions of centralizers and then take a subgroup of this. And then this implies the same result. But it also, using Andrei, Heiken, and Yaga, it also implies, and using all their technique, which basically they explained, Andrei explained me. This implies a Hahn-Neumann conjecture for hyperbolic limit groups, formulated in terms of the Euler characteristic. So, like, we take like Euler characteristic. We just take it as a sum of the Betti numbers, alternating sum of the Betti numbers, and then basically so this is the maximum of 0 and minus the characteristic, and the Hahn-Neumann basically conjecture is that if you take intersection of two finitely generated subgroups, then chi bar of A intersected mu is less or equal than chi bar of A times chi bar of B. I mean, for a free group, it is the same thing. It's the initial Hahn-Neumann conjecture for a free group, it is the same formulation. And then, Andrei, did you formulate this geometric Hahn-Neumann conjecture? Who was the first?
Maybe it was Dix.
Dix, yeah, and then it was like reformulated like in these terms, and then you can like you can consider it for a larger class of groups where this characteristic is defined. in particular like limit groups, because they have a finite invariant plane space. So for limit groups, it's a little bit like, because the result about the spaceful representation, it follows from our results with the leader which were obtained actually late, because limit groups are virtually special. But the result about extensions of centralizers, it doesn't. So for limit groups, we have kind of more corollaries. Yeah, and about quantification, I said already, so basically it's a polynomial growth with sizes of finite solutions needed to separate elements. Thank you very much.
Questions or comments?
So perhaps I did not really understand what you said about growth, because one can look at the coefficients and look at the dimension of V. They were two completely different notions, perhaps.
Depends on the subgroup, on the index, right? You have initial representation, and then you take induced representation. Dimension depends on the index of the subgroup. So basically, here the subgroup is fixed. But when the subgroup is fixed, we change elements, like element which does not belong to a subgroup changes length.
Oh, okay, I see.
And so the quotients have polynomial growth with respect to length of this length of elements, like quotient element. Everything else depends on the subgroup. It kind of it may imply some, algorithmic. It may have some algorithmic use if to work more carefully. But it is also kind of, it's nice that it is, I mean, it doesn't follow from anything else like this polynomial growth. And it is nice that it comes to the initial kind of Maltsev's ideas, basically, how to bound the quotients.
Can you say a bit more about the geometric moment conjecture? How you do it?
Okay, so this is the case of a free group. Like, I mean, in principle, like, what is the characteristics? If you have a simplicial complex, you can graph, for example, right? So this is a number of simplexes of dimension Ki is a number of simplexes of dimension I. Now, Chi bar for a free group is exactly it's a free group minus 1. So, but again, like if you start talking about limit group in terms of ranks of subgroups, this is not the right kind of, it's not the right language. And in terms of the Erlang characteristic, it sort of does make sense, even for surface groups. By the way, also this, I forgot to say, Lars Lauder, McReynolds, and Patel, they prove this for free groups, like such a representation exists and polynomial growth, and for closed surface, for hyperbolic closed surface groups. And they actually ask this question, I mean, can you generalize it to RAAGs and to three manifold groups? So, like, this theorem answers their question. And also, I forgot, there is some other team, Fisher and Morales recently put a paper in the archive where they proved geometric moment conjecture, I think for graphs of free groups with cyclic amalgamated subgroups, which also implies hyperbolic limit groups are like that. For surface groups, chi bar is going to be a rank of the group minus 2. So again, it's proves the same thing about in terms of generators. Subgroups.
Any other questions or comments? If not, let's thank all the speakers again.